So yeah, I'm Andy Harris. I'm part of Autodesk, and I'm also one of the members of the DRAMA project as well. So we've been working on that project for almost 3 years now. I'm part of the Autodesk research team. I'm located in London. We work across a large amount of industries, including medical, and I'm going to present some work later on some of the customer projects that we've completed. So just give you a little bit of background to how we came to be working in the medical industry. So originally, back in 2008, a startup called Within formed, and they were looking at, particularly in additive manufacturing, but they were looking at lattice structures and also medical devices. They had a very, very simple ethos, inspired by nature to create designs that perform, and you'll see an example of that later. And in 2014, they were acquired by Autodesk. Autodesk for a while did continue to sell the Within software, but eventually merged that onto a single advanced additive manufacturing platform called Netfabb. So if you can go on to the next slide, please. So I'm going to be covering a little bit in additive manufacturing. I'm covering specifically powder bed fusion. So we're looking at very much direct additive manufacturing processes, that being we make a part and then we use that directly in the person as an implant, rather than other indirect processes where we may want to use additive manufacturing to support something like casting. So I'll talk a little bit about the Netfabb software and some of the features that is taken from the old Within software, and then I'll go specifically into 4 customer case studies. So we can go to the next slide, please. So I'm going to start talking about additive manufacturing and why implants. So additive manufacturing has a good business case for the medical industry. You can do large amounts of customization, you can control the functionality of the parts, you can achieve things that you can't do with other manufacturing methods, such as porous structures for osseointegration, or even controlling structural behavior so that the part isn't too stiff or not stiff enough. And this image that you see here on the right, the femur, is I often show this as the reason why the software is driven by nature, why it's inspired by nature to create designs that perform. So what we have here is this femur bone, and within this we have this porous structure which is varying in density, and then we have this skin around the outside which is a varying in thickness structure around the outside, which is very much driven by the loading that the body exerts on the femur. And we replicate that in our software, so we can have varying density porous structures, we can have varying density thicknesses of skin around the outside, so then we can mimic the exact same structure that we have in the femur or in any other part of the body. So this is very much driven by the weight that the structure has to bear, and additive manufacturing helps us create these complex structures which would not be possible with other traditional manufacturing techniques. So you can move on to the next slide. So powder bed fusion, what is that? So this is basically a means of laying powder and sintering or fusing it together using a laser. So each layer is built up and we sinter or melt that using the laser, and we can do that for plastics or metals, and there are some limitations in powder bed fusion. So we have things such as surface roughness, potentially internal porosity, shrinkage or distortion, and then there's some challenges with the associated powder handling and disposal. Some of these are actually advantages in the medical industry. So things such as surface roughness can actually help with osseointegration. And there are methods that we use to encourage that. So we can apply things like trabecular lattices to the surface, which we'll see a little bit later on. And these can help with the implants fusing into the bone, so the bone can actually grow into the implant. So if you can go on to the next slide. So here are some of the technologies that are currently on the market. So we have some names here you should be familiar with, EOS being an extremely big manufacturer of additive equipment. They can utilize polymers, so such as PEEK, some metals, titanium, stainless steel, cobalt, chrome. And then you'll note there we've also got magnesium. So this is a little bit more recent development. Companies such as Equality 3D can actually additively manufacture magnesium. And some of the case studies I'll show you later, we're looking at 3 titanium applications, and I've got a magnesium application at the end as well. And you also may have heard of e-beam. Particularly one manufacturer comes to mind for that one, and that is Arcam. And with this one, you can manufacture titanium and cobalt chrome. So the image you can see at the bottom, these hip cup implants, they are manufactured on titanium, but 2 different techniques. So with laser sintering, typically from an EOS machine, or a electron beam melting from the Arcam machine. So with the laser sintering, you get a little bit more accuracy. You can form those trabecular structures a little bit better. With the e-beam, you can do things a bit faster. So if we go on to the next slide. So I'm going to talk about our common platform for advanced additive manufacturing solutions. So this is Netfabb. In Netfabb, you can do things such as preparing parts for build, but you can also use it for design and simulation. And so you can design lattice structures, you can simulate those lattice structures to understand the structural performance, and you can introduce those extra features into the surface, such as trabecular lattices. But you can also do build simulation to help remove some of those issues that I mentioned before, like distortion, any kind of shrinkage and things like that. You can help understand those issues and resolve them through compensation of the shape of the design, or new laser processing strategies and things like that. So we can go on to the next slide, please. So we can create very, very complex structures, and we've got a couple of examples of some lattice structures on the top right. There are around 25, 26 inbuilt lattice structures, but you can customize your own. So you can have completely 100% customized lattice structures that you can then start to create different structural effects. So you can have a implant that is stiffer in a single direction. You can use these lattice structures to also have a structural but also a supporting role within the build. So removing the need to have supports in the design. You can use these to control the porosity and also the surface area of the structure. So if we look to the bottom right, we have an example of the hip cup that we saw on one of the previous slides, and that's there very much to improve osseointegration by controlling the surface roughness. So what is one of the things we can also do within this software is we can actually help design those very fine structures so that the powder is still able to be removed. We can control the varying density within the trabecular structure and still have it completely 100% random. So there's no repeating patterns on there, but still also enable powder removal. So if we go on to the next slide. So we can also help with minimizing the amount of material. So by introducing those lattice structures and utilizing additive manufacturing, by using less material, you are able to also help control things like distortion during the build, but also from a medical point of view, you can actually start to control the structural behavior and also the osseointegration. There are some other benefits. So when you're inspecting the parts to see what's the status of those after they've been implanted in a person, maybe 10 years down the line, you can then start to see, oh, this magnesium part has almost dissolved into the body, or this titanium part still got structural integrity, still behaving as we expected. And we can do those kind of inspections quite easily with these structures. And very importantly, we can provide a strength and stiffness that's compatible or comparable, sorry, with the actual bone structure that it will be replacing. So if I can go on to the next slide. So how we do that, we can do this in two ways. So you have a process of being able to manually control the lattice structures and the thickness of the skin around that lattice structure. We can do that using a few different ways, things such as lattice kernels, which will be represented in the image by those orange volumes, where you're able to locally change the thickness of the lattice or the skin. You can even use them to move the lattice around if you wish. We can use our newer feature called Lattice Commander. And then we also have the lattice topology utility, where you can build customized lattice structures. We can simulate those afterwards so that you can check against other medical studies as to whether that hip cup or that femur implant is actually behaving in a similar way structurally. But we can also help you do that automatically. So driven by a simulation solver in the background, you can apply load cases to this, and you can set strength or stiffness targets on that body to then help it optimize towards, and then you can have a component that is very comparable to the bone that it's replacing. So if you can move on to the next slide, please. So this is about preparing the implant for additive manufacturing. So in the image on the top right, we have a tibial tray with support structures underneath, with the trabecular lattice on top. So that's ready to go to be additively manufactured. But it's also important that we understand how the part behaves in the additive machine before we actually start to make it. So we can carry out build simulation, and you'll see on the bottom right we've done that, and we've predicted issues like the supports detaching from the part during the build. And on the image on the left of the actual build, you can see that's what has happened. The supports have detached. So it helps you carry out these kind of studies before you actually start to manufacture the components, and help avoid some of those issues, saving you time and money. We find generally with lattice components, they don't need so much build simulation. They don't build up as much heat. They're a lot more resilient to distortion during the build as a result. But certainly for these larger parts, it's extremely important to do this kind of build simulation before you actually carry out the build itself. So if you move on to the next slide, please. So I'm going to talk a little bit about some customer success stories. So if you can go on to the next slide, please. The first one we have here is from Novak's DMA. So this is a cranial implant made from titanium. We wanted to have a porosity level of 95%, so it has good thermal conductivity, and also help with the integration of the bone with the titanium structure, and also allow the flow of liquids. So if you go on to the next slide, please. We have an implant, a facial implant, which is made from titanium, completely customized. The person that was this went into, as you can imagine, had a lot of issues with the bone structure in their face, but they needed this lightweight implant, which could basically replace that damaged bone structure. So the next slide, please. So Nuvasive, this is a spinal implant. We had to have a trabecular structure on there to encourage bone growth, but we also had to have a strength and stiffness optimized lattice in there to ensure that the spinal implant had the same structural behavior as the original disc that it replaced. So next slide, please. And then we have finally the magnesium part. So this part had to be fully reabsorbable into the body. It's a spinal implant, so eventually this part would have a finite life within the body, but it had to serve a structural performance requirements, but also we can control the rate that this dissolves into the body using controlling the surface area with the lattice structure. Okay, that's my final slide. Thank you very much.